This video is for Math 112 trigonometry, and this is for the sample final exam. So I've got the diagram from number 1 on the board already, and the problem is described. It says the person standing on one edge of the bank of a canal observes the lamp post on the other bank. The person's eye level is 152 centimeters above the ground. So I didn't label that yet, but that says that this distance right here is 152 centimeters, which means that this distance over here is also 152 centimeters. This middle dotted line is the eye line of the observer. And then the angle of elevation to the top is up here, and that's 12 degrees. Yep. And the angle of depression to the bottom is 7 degrees. And so we want to answer the questions, how wide is the canal? So that's this distance right here. And then also, how high is the lamp post? So that's going to be 152 plus whatever that distance is right there. Okay, so let's see. Here in this triangle, so the key to this is that, you know, those are right angles right there. So we're working with right triangles here. Let's see here. So beyond that, we've got this triangle here where we know one of the angles and one of the sides. That means in a right triangle we can use that information to find out the value of x, because tangent of 7 degrees is going to be 152 over x, and so x is 152 over the tangent of 7 degrees. And so, if we go ahead and calculate that, that comes out to be 1237.94. And we want to round this to the nearest centimeter, so 1238 centimeters is the width of the canal. Okay. Now you might debate about how these are set back a little bit from each side of the canal. We're not going to quibble about that. Okay. We're always looking for the best possible answer given the problem. All right. Okay. What else? Well, now that we know the value of x, we've got another right triangle here, and we can say that the tangent of 12 degrees is a over, you can use 1238 if you want. I like to use the most accurate number possible, although the scientists will debate me about the importance of significant figures. So, in any event, what I'm saying is you can use 1238, you can use 1237.94, or I've got the whole thing sitting right here. So I'm just going to hit times tangent of 12, and that'll give me an approximate value for A of 263.132. So to the nearest centimeter, A is 263. But again, that's not the answer to the question, because that's just this portion up here. So the full height for the lamp post, that is going to be, what is that, 415. Okay. All right. Now, if you had just left it at 263, I'd give you the majority of credit for this question. But I would probably take a point off for not adding it to the 152. So the answers here for full credit are 1238 and 415. Okay. So that's problem 1. Now let's take a look at problem 2. Okay. All right, so let's see here. We've got one mountain here, a couple more, and then another mountain here. So that's A, that's B, and then we've got this helicopter here, like this, hovering hovering 1,500 feet directly over peak A, which we know the altitude for. And then, let's see here, we've got a series of lines drawn in here. We know that this angle is 15 degrees. We know that this angle up here is 50 degrees. And what are we being asked for? Find the distance between the two mountain peaks. So that's this distance right here. I'll call that x. And the approximate altitude of B. Well, the altitude of B, so we know that this distance right here is 4,800 feet. And then again, this distance here, I'll call it A. We're going to find out what A is and then add it to 4,800 feet. Okay. Now this one is a little bit tricky. Let's see. This is a right triangle right here, but we don't know any of the sides in that right triangle. We know an angle, 15 degrees, but we don't know either of the sides. The only length that we have is this one right here, 1,500 feet. Now, the key to this is that these are right angles, okay? Which means that if this part is 50, this part's 40. And if this one is 15, then this one, I believe, 75? Yeah. All right. So now, in this triangle, we've got a side plus, and we have two angles, so we can calculate the third angle if we want to. Let's see, what is that? 40 and 75 is 115. 180 minus 115 should be 65 over here. Okay, so now we've got all three angles in this triangle plus one of the sides, so we can go ahead and find out one of the other sides. We want to know what that value of x is right there. So, let's see here. We can say, we can use the law of sines. X over the sine of 40 equals 1,500 over the sine of 65 degrees. Okay, so now, let's see here. We're going to do 1,500 divided by the sine of 65 degrees, and then multiply by the sine of 40. And that tells us x is going to be 1,063.86 approximately. And what are we rounding to here? To the nearest foot. So this is going to be 1,064 feet. And we don't have to do anything else to that. That is, x is that distance between the two mountain peaks. Okay, well now that we know that, now we can go into this right triangle right here and say that the sine of 15 degrees is going to be A over this value. And again, you can use 1,064 or 1,063.86. The important thing is that your final answer rounds to the correct value. Okay? So I recommend using the more accurate numbers until you get to that final step. That's the point where you should round off. This difference here, it probably shouldn't make a whole lot of difference in this particular problem with these particular numbers, but that's not always the case. All right, so, and actually I'll calculate this and see if we get any noticeable difference. So let's see. So we want to multiply this 1,063.86 times the sine of 15, and that tells me that A then is going to be about 275.35. 275.35. That's in feet. And so we can add that to the 4,800, right? So that we get the full height of B. And that gives us, what is that? 5,075 to the nearest whole foot. Okay, and that's the point where you should round off. Now, what if we did 1,064 times the sine of 15. That's 275.38. So yeah, we see a difference in the hundredths place, but if we're rounding to the nearest whole number, then it's not going to make that much difference, okay? But like I said, that's not always going to be the case, and so I encourage you to be careful with your accuracy and your rounding. And let's see, I think we answered both of those questions to the nearest foot, and so that's it for number 2. All right. Oh, if you're taking the test and something in the diagram is not clear to you, you can ask me. You know, if I've left something out, I'll answer your question. If it's something that's part of the test, I can just tell you that I wouldn't be able to answer your question. Okay. But I'm not trying to discourage you from asking. I you know, don't want to give answers away while people are in the middle of taking the test. Okay. Problem 3. Before I go ahead and do problem 3, I just wanted to point out the last page in the sample final exam is the same as the last page in the actual final, and this is your formula page. At the top, you see it's just the same as it was for the midterm. You've got the sine, cosine, and tangent definitions. You've got the graphing information about how it affects the x and y axis. And then underneath that is the new stuff for the final. You've got all the trigonometric identities that we talked about, and then at the very bottom of the page we've got the law of sines and the law of cosines. And that will be, like I said, that'll be attached to the back of the final exam. You don't really need to put those onto your note card. In fact, that would probably take up most of both sides of a note card. So yeah, that wouldn't leave much room for anything else. So yeah, you should put whatever you want on your note card. You're not going to need to put those formulas on it because I'll provide them to you. All right, problem 3. Problem 3 is a little bit tricky, but we'll try to make sense of it for you, or help you to make sense of it. Ship leaves a harbor traveling 15 miles an hour along a bearing 24 degrees east of south. All right, so let's start there. Let's do our north, south, east, and west diagram. 24 degrees east of south would look like that. It's going 15 miles an hour for 2 hours, and so the length of that piece right there is going to be 30 miles. Okay. At that, let's see, the ship then proceeds along a course with a bearing of 37 degrees east of north for 5 hours. All right, so we've got to do another north, south, east, west. Okay, because the bearing is given from this position. We don't go back to this one again. Okay, and so from that position, they go in the direction 37 degrees east of north. It's going to be something like that. And I drew that line longer because they're traveling for 5 hours in that direction. So that line will be 75 miles. Okay. And this angle in here, 37 degrees. Okay. How far is the ship from the harbor? So that's going to be this distance right there. I'll call that x. And what bearing should the ship take in order to return to the harbor? So I'll get into that in just a second. First off, let me redraw this triangle. It's going to look something like this. We know this side is 30, this side is 75. Now we need to know some of the angles in here. We don't have a lot of information other than this angle and this angle, neither of which is a full angle in the triangle. Okay, so how can we get that? Well, you remember when I was talking about alternate interior angles, I talked about the importance of recognizing that z, okay? because here it is right here. Now it's in two different colors, so I don't know if that makes it harder to see, but there's the Z right there, which means that if this is 24 degrees, so is this one in here. They're alternate interior angles. Okay? So that says that this angle in the triangle now is 61 degrees. Okay. So now we've got two sides and an angle between them in this triangle, which says that we can use the law of cosines to find this value x. So we'll say x squared is 30 squared plus 75 squared minus 2 times 30 times 75 cosine 61 degrees. All right, so 30 squared, 900, 75 squared, 5,625, 60 times 75, 4,500 times the cosine of 61. So 900, 5625, 6525 minus 4,500 cosine 61, 2181. 0.64. So 6525 minus that, x squared is going to be about 43.36. So let's square root that, and that says that x is going to be approximately 65.9 miles to the nearest tenth. And that's the answer to the first part of the problem. Okay. Now, in terms of what bearing should the boat take to get back to the harbor? All right. Well, now we need another north, south, east, west setup. Okay. So it's clear that we need, well, what we need to know is this distance, or that angle right there, because it's going to be that angle west of south. But we need to know that angle. Part of it is inside the triangle, all right? And so we can find this angle right here, but let's see, what do I want to call that angle? I haven't really used any variables, so I'll just call it angle A. So we'll say the sine of A over 30 equals the sine of 61 over 65.9. Okay, so let's go ahead and see if we can solve this one. Let's see what we've got here. So, sine of 61 degrees divided by 65.9 times 30, 39816. Okay, now let's see if we do the inverse sine there. That says that angle A is 23.46 degrees. Okay. Now, I'm using the law of sines. I do have to be careful about that ambiguous situation. But notice that the side across from A is significantly smaller than the side across from the 61 and the side across from the 65. In fact, this is the shortest side in the triangle, so there's no way that A could be an obtuse angle. So we don't have to worry about that ambiguous case of the law of sines. We've got some confidence that angle A is just going to be 23.46 degrees. But that's really just part of what we need, right? We need this whole thing right here. And like I said, the 23.46 degrees is a part of that, but it's only a part. It's not the whole thing. So how do we get this little piece right here? And the answer is, here's another Z, okay? Those are both this 37 and that angle in there that we need to know right here are alternate interior angles. Okay, there's the Z, like that. It's a little bit funky, but that allows us to find the bearing, okay, that the boat would need to take to get back to the harbor. It's going to be 37 plus that 23.46, and what is that, 60.46? Okay. Let's see here. For some reason in my notes I have 0.45. I mean, I'm off by 1/100th, and in those situations I typically don't take points off, but I am curious where that difference is coming from. Okay. I guess, well, the 45 is more accurate. 46, I think, came from the fact that this 65.9 is rounded off. Okay? And that's the reason why, if you round to the place that I'm asking, and you're off by 1 unit in either direction, I don't take points off for that. Okay? Because it's easy to have that happen to you. But if you're off by more than that, I start looking for why that is. All right? So, in any event, this full angle right here with the purple, that is 60.46 degrees. And so we want that 60.46 degrees west of south. And that's how the boat can get back to the harbor. Okay, so you can see these word problems typically use, fairly involved combination of right triangle trigonometry along with the law of sines and the law of cosines. It's good. You're going to have a problem very much like this on the final, so it's good to have a pretty firm grasp of how these bearings work, and when you start drawing these multiple diagrams, to recognize the alternate interior angles that are going to come up as a result of that, so that you can find the values for angles that you need to know. Okay, that's it for the word problems. So let's move on to problem 4. All right, these should be graphing problems. Okay. Problem 4, we want to graph y equals 6 minus 2 sine 2/3 x. All right, so let's see here. So if our standard equation says y equals a sine bx plus c plus d, then the a is the 2, or -2 here, all right? The d is the 6, right? It doesn't matter whether you write plus d or d plus, that's still the vertical displacement, okay? So that says that our midline value along here is going to be 6 with an amplitude of 2. It'll go up to 8 and down to 4, okay? Now, notice there's no value for C. That means there's no phase shift back and forth, right? This graph is going to start at 0, all right? What we need to know is what's the period for it, and then we need to split that period up into 4 pieces, okay? So, from the formula sheet, the period is 2 pi divided by b, which in this case is 2/3. If you're going to divide by a fraction, it's important to have parentheses around it. I'm in the habit of multiplying by the reciprocal, which gives us a period of 3 pi. Since there's no phase shift, that means our graph is going to end at 3 pi. Now, there's a couple different ways to do this. If you're starting at 0, you can just cut this in half, cut it in half again, and that'll give you these values right here, right? So this one is 3 pi over 2. Excuse me. That one is 3 pi over 4. So each of these jumps is 3 pi over 4, and we could have gotten that by just taking this and multiplying it by 1/4 as well. So it's going to go 3 pi over 4, 6 pi over 4, 9 pi over 4, and 12 pi over 4. So there we are. Now the last thing here is that this is a negative cosine. So it's going to start at 0, but then it's going to go down to the minimum, back to 0, up to the maximum, and back to the midline value. And so there's our graph for number 4. Okay, let's see here. All right, let's look at number 5. Now number 5 does have a phase shift in it. That's going to be a little bit trickier. All right, problem 5. Y equals cosine 3x plus pi over 2 minus 1. All right, so here notice that A is 1, D is negative 1. So that D is going to be our midline value. And then on the y-axis, we're going to go up 1 to the maximum, down 1 to the minimum. Okay, so there's that setup. Now, for the x-axis, let's get our starting point first. We can set this equal to 0. 3x plus pi over 2 equals 0. 3x is negative pi over 2. Divide on both sides by 3. X, the starting point here is going to be negative pi over 6. Okay? Now, where are the jumps? How far are those jumps going to be, right? We've got our starting point here at negative pi over 6. Each one of those jumps is going to be the period divided by 4. So we need to know the period. 2 pi divided by b, and b is 3. So there's our period, 2 pi over 3. Each of these jumps is 1/4 of the period. So 2 pi over 3 times 1/4, 2 pi over 12, which is pi over 6. Well, that's really helpful, because if you go 1 pi over 6 from negative pi over 6, that will bring you to 0. And then positive pi over 6, 2 pi over 6, and 3 pi over 6. Now these have to be reduced. I'll do it in a different color here. So rather than leaving this 2 pi over 6, you want to call it pi over 3. And rather than calling this 3 pi over 6, you want to call it pi over 2. All right. So let's see here. So there's our 0, positive pi over 6, positive pi over 3, positive pi over 2. It's a positive cosine, so we start at the maximum, midline, 0, midline, back to the maximum, and there's one period of our cosine graph. Okay, so that's it for the graphing. We just have 2 of those. And then, let's see, next is the identities. Okay, let's take a look at those. Problem 6. Tangent theta plus cotangent theta equals 2 over sine 2 theta. don't see any squares in this initial expression. Okay? And so that says to me that we probably won't be using those Pythagorean identities right away. All right? The immediately obvious identity I see is sine 2 theta. So we can go in and write this as 2 sine theta cosine theta. And if we do that, these 2's cancel each other out. Remember, that'll leave a 1 in the numerator and sine theta cosine theta in the denominator. Now, seeing that, that says to me that the strategy of rewriting everything in terms of sines and cosines could take us here. Okay? It's never a guarantee. There's no guarantee that one of those strategies will work over the others. But, you know, you just have to go on your best instincts. And that's why I think it's a good idea to do a lot of these problems. That's how you help develop those instincts. All right. So I'm going to rewrite these in terms of sines and cosines. This one, sine theta over cosine theta. And this one, cosine theta over sine theta. All right. So now that we've got that, we've got two fractions. We should make a common denominator for them and add them together. So this one needs to get multiplied by sine theta over sine theta. This one by cosine theta over cosine theta. And so that'll give us a new common denominator of sine theta cosine theta. Great. Same denominator that we have over here. On top, though, we get something a little bit different. Sine squared theta plus cosine squared theta. Ah, now we need the Pythagorean identities. And we say this is 1 over sine theta cosine theta. And I do need to see that last step. Okay? If you just leave it like this, I can assume that you know that this is equal to 1. But the whole point of a test is for you to demonstrate that you know that this is equal to 1. And that's how you can demonstrate it, is to take that extra step and lay it out for me. Okay? So, that's it for problem 6. Let's take a look at problem 7. All right, let's see here. Problem 7. Tangent x equals cosecant 2x minus cotangent 2x. Okay. Well, we may in the end rewrite this as sine x over cosine x, but for right now I'm going to leave that alone. I'm going to focus on these because we don't have identities for these, okay? But we can rewrite them, I mean we can use a slightly different identity as reciprocals. So 1 over the sine of 2x minus cotangent is going to be cosine 2x over sine 2x. Nice, we don't have to make a common denominator. And so that's where that takes us. Well, at this point, I would replace these with their identities. Okay? And so in the denominator, we get 2 sine x cosine x. Now in the numerator, the cosine 2x, you've got choices, right? Well, whenever I see a 1 here, I choose the version, if I can choose a version that will cancel this 1 out, I try to do that. So let's see, 1 minus 2 sine squared x. Get confused between my thetas and x's here. There we go. So this is going to be 1 minus 1 plus 2 sine squared x over 2 sine x cosine x. So these 1's cancel each other out. Then we've got 2 sine squared x over 2 sine x cosine x. Now notice there's no pluses or minuses in the top or the bottom. That allows me to cancel out those 2's. And this sine x will cancel out one of these sine x's to make this sine x over cosine x. And there we go. Tangent x equals tangent x. Okay. Well, That's problem 6 and 7. We got one more identity here. Problem 8. Secant squared alpha times the cotangent of alpha minus cotangent of alpha equals tangent of alpha. All right, well, there's a lot of choices you can make here. The secant squared is going to be 1 plus tangent squared. You can also factor out a cotangent from here. And then you can also rewrite everything in terms of sines and cosines. Those are 3 different approaches to solving the problem. I wouldn't use all 3 of them in the same solution, right? Those are 3 different ways to start. So let's see here. So if we started, I'll do a couple of them. So if we started by rewriting this as tangent squared alpha plus 1 times cotangent alpha minus cotangent alpha is tangent alpha. All right, so this would give you, if we distribute the cotangent into the parentheses, that'll be cotangent alpha times tangent squared alpha plus cotangent alpha minus cotangent alpha equals tangent of alpha. So these right here, very quickly, cancel each other out. Over here, let's see, cotangent alpha is 1 over the tangent, right? You can rewrite them in terms of sines and cosines if you want to, but there's really no need to do it. What you've got is 1 over tangent alpha times tangent squared alpha. That's going to cancel one of these, and there's your tangent alpha equals tangent of alpha. So that's one way to approach this. The other thing that you can do, factor the cotangent out, and that'll leave you the secant squared alpha minus 1. And then if you go to your identities, secant squared alpha minus 1 is the equivalent of tangent squared alpha times cotangent alpha. And now we're just back to this part right here, right? This is 1 over the tangent. That'll cancel out one of those tangent squareds. And there's our tangent alpha equals tangent alpha. Okay, I'll just leave it at that. There's a third way to do this, but in the sake of time, I'm not going to go into it. But it's every bit as correct. You know, that's the thing about solving identities. That's why there's no answer key for those first couple sections in Chapter 3, is because there's so many different ways to solve these. Because we weren't having class in person, I tried to provide you with at least one viable method of solution. But there are multiple valid methods of solution for these identities. All right. Last page here, problems 9, 10, and 11. We've got these trigonometric equations. So let's go ahead and work on these. You're going to need to be solving the quadratic formula. If you've got it programmed into your calculator, that's going to be very helpful. If you haven't done that, I'll tell you the quadratic formula if you need to know it to solve these problems. Like I said, I suggest that you program it into your calculator, but if you don't, I'll give you the quadratic formula so you can at least solve these equations by hand calculation. All right, problem 9. Sine squared x plus 2 sine x minus 2 equals 0. Well, this is a quadratic equation in standard form, so there's not a whole lot that we need to do to it to get started. A is going to be 1, b is positive 2, c is negative 2. So given that, we can run that through the quadratic, positive 2 and negative 2, and this says sine x is going to be about 0.732, or sine x, and I wouldn't rounded off there. I mean, I suppose it's okay. I would probably go at least that far. It's good to have at least 4 places if you're going to have a trigonometric function. The other one, negative 2.732. No real valued angles have sines or cosines more than 1 or less than negative 1. So this is not going to give us a real valued answer. This is the one that we're interested in. We're going to do the inverse sine. Let's see here. What if I put 732? Yeah, 732 is actually a pretty good approximation. And that's mostly because of this 0 following it. Either way, well, it'll be off in the hundredths place. But here we're rounding to the nearest tenth of a degree. So this is going to be 47.1 degrees. Okay, and then we go to our diagram. The sine is also positive in the second quadrant. And so we want to do 180 minus 47.1. Gives you 132.9 degrees, and there are our real value solutions. Okay, that's problem 9. Problem 10. Cosine 2x minus sine x equals 1. Okay, so the idea here is that we're going to have an identity that's going to allow us to replace cosine 2x with something else that can help us to solve this equation. And, you know, we've got 3 different identities for cosine 2x. We want the one that's going to match up to the sine x, which is already there. So that means we're going to want the identity that says that cosine 2x is equivalent to 1 minus 2 sine squared x, and then minus sine x equals 1. So let's see, I'll subtract 1 on both sides. Those cancel each other out. And then I'll move these to the other side. You don't really have to do that, but I find it less confusing to at least have the leading coefficient be positive. Okay, so we can run this through the quadratic with a equal to 2, b equal to 1, and c equal to 0. You can also factor the sign out. Okay, I'll do that in 1 sec. If we run this through the quadratic, let's see, 2, 1, 0, we get sine x equals 0, or sine x equals negative 1/2. Okay? If we were to factor it out, pull out a sine x, that'll leave you with 2 sine x plus 1. So there's your sine x equaling 0. 2 sine x plus 1 equals 0. So sine x is negative 1/2. Okay, same answers. All right, let's do this one first. We're going to do inverse sine negative 1/2. And that's going to be, negative 30. X is negative 30 degrees. But remember, we're looking for solutions between 0 and 360. This is not between 0 and 360. Okay? So we've got to find angles that are between 0 and 360 that also have a sine of negative 1/2. So the sine is negative in the 3rd and 4th quadrants. So we want to look for reference angles of 30 degrees in those 2 quadrants. 360 minus 30 is 330 degrees. 180 plus 30 will give us 210 degrees. So there's those 2 solutions. Now here's the thing. When you do inverse sine of 0, you get an answer of 0 degrees. And that is correct. But we're missing one solution here, okay? And this goes back to, number one, the limitations of technology. Technology is very helpful to us. However, every piece of technology has limitations. And it's our responsibility as human beings to understand those limitations and to compensate for them. All right, what am I talking about? Here's the unit circle. These points are 1, 0, 0, 1, negative 1, 0, and 0, negative 1. They also represent the cosine and the sine of whatever angle is here. So here, this is 0 degrees. This is 90 degrees. This is 180 degrees. And this is 270. So, the sine is the y value. 0, 1, 0, negative 1. So notice that 180 degrees also has a sine of 0. And that's our final answer to this 0 degrees, or 180 degrees, or 330, or 210. Okay? So there's problem 10. If you leave off that 180, that's a very small error. Okay? I'm not backing off what I said about making up for the limitations of technology. That is important. But I also don't believe that you should lose a substantial portion of the credit just because you missed that one answer. Okay? So I think it's valuable to know how to get it, but I wouldn't take off any more than 1 point if you left it out. Okay? All right, that's problem 10. I think we got one more to look at. Problem 11. Okay. Problem 11. 2 secant squared x plus tangent x equals 3. All right. So again, we need an identity that will turn this into a solvable quadratic equation. Well, we've already got a tangent in here. We don't really have an identity for that, okay, other than sine over cosine. That's going to take us into a more complicated situation rather than a less complicated situation. The secant squared has an identity that will match up with the tangent very nicely. It's important to put it into parentheses. Tangent squared x plus 1 is secant squared x. And then we've got plus tangent x equals 3. So, 2 tangent squared x plus 2 plus tangent x equals 3. Subtract the 3 on both sides. That'll give us 2 tangent squared x plus tangent x minus 1 equals 0. And this is factorable too, but we can go ahead and use the quadratic formula. Let's see here. So A is 2, B is 1, C is negative 1, and that gives us solutions. Tan x equals 1/2, or tan x equals negative 1. Okay, so let's see here. Inverse tangent of 1/2. Inverse tangent of positive 1/2 is 26, we're rounding to the nearest tenth here, 26.6 degrees. And then in our little diagram here, the tangent function is positive in the third quadrant. Put a reference angle of 26.6 in there, and then add 180, and we get 206.6 degrees. So there's 2 of our answers. Take the inverse tangent of negative 1. The calculator returns a value of negative 45. Again, not between 0 and 360. Okay? So we need to turn this into answers that are between 0 and 360. Where the tangent is negative. So that's going to be in the fourth and second quadrants. Okay? Tangent's going to be positive in the third and in the first. So, well, these are actually 45 degrees, so why don't we draw it so it looks like 45 degrees, which means it's going to cut right through the middle. There's that reference angle, and there's that reference angle. This one is 360 minus 45. That's 315 degrees. This one is 180 minus 45, which is 135 degrees. And there's all of our answers. Okay? So you can see with these problems, sometimes you'll get 2 answers, sometimes you'll get 3 answers, sometimes you'll get 4 answers. It depends on the problem. Okay? All right, so that's it for the sample final. Your final exam will be remarkably similar to that one. It'll have the same number of questions, the same types of questions, but different questions. As always, if you have any questions about what I was doing up here and going over these problems, or about your project, please let me know. Thanks a lot.